So when it comes to integration, you already know how to find the area between a curve and the x-axis on various different areas and stuff by using integration and something limited. What we're going to do now is extend this idea, and instead of just using it to work out areas, we're going to use this to work out volumes. And the volumes that we're creating are going to be rotated around either the x-axis or the y-axis. Okay. So this is example 1 in your pack. So this is the graph y equals 4 minus x squared. And example 1 asks you to find the exact volume of the solid formed when that area is rotated 360 degrees about the x-axis. I'm going to show you what that is using this so you can sort of visualize it a bit and hopefully help you. And then I'm going to derive a formula that we're going to use. Okay. So we're going to take this purpley pinky, what we'll call it, area this is, and rotate it around the x-axis. Okay, so I'm taking that area and rotating it around the x-axis. Okay, rotating all the way around there. A bit like an M&M's Skittle minstrel song. Always makes this. Okay. This is the volume that we're going to be working out. It's not really related to the area as such. It's not like you work out the area and then times it by something. We're going to do it a bit different. And the way we're going to do it is using this formula here. Now, ultimately, this is a formula that you need to learn. It's not on the formula sheet. You do need to know it. I'm going to show you where it comes from, which you might occasionally get asked questions. So if you look at this diagram here, on this here this is kind of that integration from first principles stuff that you did in the integration pack a while ago. So you remember when we did that, you split it up into rectangles, and you take the limit as the width of the rectangle turns to 0, and the limit of that sum turns into an integral. Works similarly sort of here. So we're taking this area and splitting it up into rectangles. Now, if I was to take this first rectangle and rotate it around the x-axis, what shape would you get? Cylinder, yeah. So if I take this rectangle and rotate it around the x-axis, I get a cylinder. And I'm going to take all of these rectangles, rotate them all around the x-axis and get a bunch of cylinders. And if I add up their volumes, I'll get the total volume of the shape. Okay. You know the formula for a volume of a cylinder is pi r squared h. In this case, so taking this rectangle and rotating it around, it's got a width delta x. That corresponds to the height of your cylinder. If you imagine rotating around, that's the height of the cylinder, the thickness of the cylinder. The radius is this length here, the height of this rectangle, which is y. So in terms of this thing here, the volume of this cylinder is pi y squared delta x. Okay. If I do that for each of the rectangles and add it up, it turns into this sum here. So approximation for that volume is the sum of pi y squared delta x. And if I take the limit of this as delta x tends to 0, just like you did in the integration pack, the limit of the sum turns into an integral. And that's where this formula comes from. Okay, so if you ever forget it, it's the volume of a cylinder. So pi y squared dx pi r squared h. So those bits come from. The limits of the integral are the start and the end of your interval. Okay, so a is here and b is here on your diagram. Okay, you need to learn this, but that's where it comes from. It comes from adding up a bunch of cylinders. Okay. Importantly is which axis you're rotating around. So the dx bit tells you that you're rotating around the x-axis. Likewise, today we're also going to do rotating around the y-axis. It'll be a similar sort of thing, but it'll have x squared dy instead. So dx is y squared dx is around the x-axis, x squared dy is around the y-axis. Okay. So I'm going to work through example 1, and then I'll get you to have a go at the U triangle. First thing to do, write down the formula. So volume rotated around the x-axis is pi times the integral of y squared dx. I'm just going to put that word of doing it between a and b. We've just got y is 4 minus x squared. So if I substitute this into here, this is integrating 4 minus x squared. And we also need to work out our limits. In this case, because it's the area enclosed by the curve and the x-axis, I need to find where it crosses the x-axis. Have a look at this. The limits of this area is between where it crosses the x-axis. So if I set this equal to 0 and solve it, I get my limits at plus and minus 2. So minus 2 on the bottom. So that's just for this one because it's enclosed by the curve and the x-axis. You might have different ones, but the important thing is these are always x values for rotating around the x-axis. We're going to do this integration now. I can't integrate it as it is because it's not linear inside the bracket. Because it's just a bracket squared, I'm just going to expand it out. It's not too bad. So expanding this out gives me 16 minus 8x squared plus x to the 4th. And what's an easy mistake to make is that once you've expanded it out, you feel like you've finished and then you start summing stuff in. Don't forget to integrate it. It's really easy to forget. So integrating this, just A1 integration, just adding 1 to the power and dividing by the new power. So it's 16x minus 8 over 3 x cubed. It's a fifth. X to the 5. Make sure you keep your pi all the way through as well. It's really easy to lose the pi. Finally, I'm solving my limits and I'm going to work it out. Please make sure you show your substitution into your limits. It's important for getting all the marks in the exam. Especially if you make a mistake, you'll still get the method marks if you show the substitution. Keep the pi out the front. Subbing in 2. And then subbing in minus 2 and taking that away. I'm then just going to work it out in my calculator. I'm going to leave the pi off because I want it exactly. I'll probably do it anyway. So I've got 16 times 2 minus 8 over 3 times 2 cubed plus a fifth and 2, 5. And then minus, put that in a bracket, all of that. So 16 times minus 2 minus 8 over 3 times minus 2 cubed plus a fifth minus 2. 5. That gives me 512 over 15. Pi, it asks for the exact value, so I should leave it like that. You could always type the integral in your calculator to double check you get the same answer as well, but it's always worth subbing these in just to make sure that you haven't made any slips with thousands. Okay. Have we got the U try, please? Be really careful. It's harder to get the exact answer on the U try, because you've got to be really careful with the powers. If you please try and get the exact answer. If you really struggle, I'll accept a decimal, but do have a go at getting the exact answer first. So now we're doing rotations around the y-axis. It's very much the same formula, except the only thing that changes is instead of y squared dx, we've got x squared dy. Okay. And again, remember, it's that dy bit that tells you what axis you're rotating around. When you're rotating around the y-axis, you've got dy there. Okay. When we're rotating around the x-axis, you needed x values for your limits. When you're rotating around the y-axis, you need y values for your limits. Usually you'll have to rearrange your equation to make x or x squared the subject before you do the integration. If you have to do this on a quadratic, if you need to make x a subject of a quadratic, you'll usually be required to complete the square and then get it that way. Okay, well, that doesn't come up all that often. So look at the volume for this example here. So this example, this is the graph from example 2. We're taking this green area and rotating it around the y-axis this time. So rotation this around the y-axis going that way. That's quite interesting. Makes that kind of similar paradox shape. I don't know if you can see the question with the curve side on the symbol. Wait, so that's the volume we're working out here. So this one less tricky than the last one. We've got y equals 2 over root x for our curve here. We need to make x a subject of this, which isn't too hard for this one. So I'm going to swap the x and the y. So it's that y equals 2 over root x. We've got root x equals 2 over y, and I'm going to square it to make x a subject. X for. It then tells us rotated 4 right angles about the y-axis, which forms a whole turn. They just word it weirdly sometimes. To form solid S, and wants us to show that the volume of S is that there. First off, write out the formula. So V equals I times the integral of x squared dy this time, because we're rotating on the y-axis. And our limits are our y values at this point, so 1 and 2. Be careful, sometimes they give you x values when you need y values, so you might have to put them into the equation to work. We've made x a subject, so we can substitute that in. So integral between 1 and 2 of 4 over y squared. Don't forget to square that again. It's really easy to think, well, I squared it here, so I can flip it in. But you need to square it again because it's x squared. So we're integrating between 1 and 2, 16 over y to the 4. Or to be able to integrate it, I'm going to write this as 16y to the minus 4. With this being a show that question, it's even more important that you show all the substitutions and everything, because they'll expect to see that. We're going to do this integration, add 1 to the power and divide by the new power. Remember my pi. Yeah. So adding 1 to the new power gives me y to the minus 3, and divide by minus 3 gives me minus 16 over 3. Limits of 2 and 1. Show the substitution, so minus 16 over 3 times 2 to the minus 3. And minus 16 over 3. 1 to the minus 3. That's enough. You don't need to show the fractions. You can just get down to that stage and type it into your calculator. That's okay. So I'm going to do it without the pi. Minus 16 over 3. 3. And then minus 16 over 3. 1 to the minus 3. Which gives me 14 over 6. If you want units, you can put units cubed, but you don't have to. You won't get marks.